In this video, we're going to be talking about how do we determine if something is an inverse function, how do we understand if two functions are inverses, and how can we tell if we're given a function if it can even have an inverse function. And one of the key terms we're going to learn here is one-to-one. So I'm going to fill in this blank space here. So a function has an inverse if it is one-to-one. And what that means is just on like a table scale is you can tell if something is one-to-one if all the x values don't repeat, just like how we tell if something's a function or not. So the x values cannot repeat, but also the y values can't repeat. And that's how you could tell from a graph or sometimes even on a table. But another way you can tell on a graph is if something's one-to-one is something called the horizontal line test. Just like the vertical test, a horizontal line test basically means that when you graph something, it can't hit the graph more than one time. So to just show you guys a quick sketch, if you had a graph, and let's say your graph looked like, let's say like this. So this here would not be one-to-one because this would hit it in three places because we're using the horizontal line test now and it's hitting in 3 places. Whereas like, let me draw one that actually could work. Like a line could work. If you were to draw a line and use the horizontal line test, well, it would only hit it one time on the graph, and so this will pass the horizontal line test, which means that it is one-to-one. So just to summarize things, one-to-one functions pass a line test. Oh, sorry, I wrote test twice. Let me erase that. And thus, one-to-one functions do not have repeated y values, and that means that for every given x value, it has a unique y value that is associated with. So let's say x equaled, so x is -1 here and the y value was 2. Well, that means for any other x value, it should never equal 2 for y again. So another thing is you can verify if functions are inverses if you find the composition function. So plug g into f or f into g and you spit out just x to the first power. So if you take the composition function and you get x out, then you know that those two functions are inverses. That's only when you're given two functions. Like in example 3, you're going to be given two functions. So that's how you can evaluate. So first, let's start with example 2. So it says, consider the table. Is it a function? Is it one-to-one? Does it have an inverse? If so, find it. So first off, let's answer the first question. Is it a function? Well, something's a function if the x's don't repeat. So in this case, when I'm looking through the x values, none of the x's repeat. So yes, this is definitely a function because there are no repeated x numbers. Is it one-to-one? So if you know something is one-to-one, that means every x value had its own y value. It was not repeated. So in this case, -7, there's no other 7s here. For this 2, there were no other 2s here. -3, there were no other -3s. So, and so forth. Every x value has its own unique y value. So this is definitely yes, and that's how I tell if something is one-to-one. Basically, none of the x's repeat and none of the y's repeated. So in this case, this is definitely an inverse because it was one-to-one. So I'm going to say yes. And so if it is an inverse, you have to find the inverse function, and that's relatively simple. Again, if you remember, this f of x is really just y, so all you have to do is make a new table. Do my best. Let's see, how many columns did we have? So I'm going to call this my x, this my y, and so this is my inverse table now. So all I'm going to do is switch the x's with its y's from the original. So I'm going to take this here, the y values, and make it my x values. So that's going to be 7. So I would have to put them in order, probably. So I'm going to put them in order. So it'd be -1, 1, 2. Let me cross out the ones I do, or else I'm going to get confused. 4, 5, and 7. And so remember, you're going to have to make sure you use the correct x value. So this was negative 3. So my y value here was negative 1. So negative 1. And then for 1, it was 0. So I'm going to put a 0 here. And for 2, it was negative 3. For 4, it was a 1. And then for 5, it was a 3. And for 7, it was a negative 9. And so there we go. We have our new table. So essentially for tables, just switch the x and y values, but make sure they correspond with each other. And yeah, that was it. So then for the next one here is consider your function x squared. So this is a parabola or quadratic. Is it 1-to-1? Can we make it into 1-to-1 by restricting the domain? So first of all, let's draw a quadratic function for a sec. A quadratic function looks like this, facing up, right? So when I look at this, I am going to use the horizontal line test and just draw me a horizontal line, but I hit it in 2 places. So that means it fails the horizontal line test. But let's just understand it from a deeper perspective. If x equals negative 1, that means that it would have equaled, it would have hit it at 1. If x was positive 1, it would also have hit it at 1. So in this case here, x has not a unique y values. So when y equals 1, x could also be negative 1 and positive 1. So there's basically, this is not 1-to-1 because it fails the horizontal line test. So in this case, no. So it's not 1-to-1. Can we make it 1-to-1 by restricting the domain? Yes, so you can do this. So what you can do is restrict the domain to half of it. So what I mean is if I pretend, say for a moment, to just use the left side of the parabola, so from 0 to negative infinity, then I can say that this is 1-to-1. If I do a horizontal line test, it will pass. Same thing if I were to restrict the other half, maybe from 0 to positive infinity, then this can also pass a horizontal line test. It doesn't matter which side you choose, but you can make it 1-to-1 if you restrict the domain to basically half of the domain. So I'm going to say yes. Yes, if you, let me zoom out for a sec. If you restrict the domain as x greater than 0, so in this case from 0 onwards, you could restrict it this way, or you can restrict it as x needs to be less or than equal to 0, or this guy here, so from negative infinity to 0. So you can either write it this way, or you can say the domain needs to be from 0 to infinity, or the domain needs to be from negative infinity to 0, and you can restrict it that way. Oh, I think I should have used brackets, my bad, since that was an inequality. So this here, I wouldn't give you a problem like this on the quiz, but I want you to think about it deeply, and so that's why I'm talking about how you can take an equation but also restrict it if you want to force it to be an inverse function. All right, let's talk about number 3 here. So number 3 is talking about, are the functions inverses? If you're already given 2 functions, so you're given an f, you're given a g, you have to show if they are a function or not. So you can, I know it says you can show it algebraically and graphically, but in this case, we're just going to show it algebraically. I'm not going to worry about doing it graphically, but you can graph it and see if it reflects off the y equals x axis. But I'm not going to do that here. So I'm going to teach you how to do it algebraically, and it's using the definitions up above where you're going to find the composition function. You're going to plug g into f or f into g and find if you get out just x to the first power. If you do get this, then you know it's an inverse. So it doesn't matter which one you choose, which version you choose. only that you do one. So I think personally, do whichever one is easier. So for A, personally, it doesn't matter which one I plug in. I'm just gonna choose F plug in G, kind of minusly, just to show you how to do things first. And then I'll teach you more strategies. So if I were to plug in G, remember from last time, so G is actually X minus 1. So I'm going to replace this guy with X minus 1. So I'm going to write F, and my G is X minus 1. And so that means I'm going to plug all of this in for F. So if I go to the F function, the only X that I have is this X that's next to the 2. So when I'm rewriting F, this is going to be 2. Instead of this X, I'm going to have all of this stuff. So this is going to be X minus 1 over 2 plus 1. Now I know this looks crazy for a moment, but think of this as a fraction. That denominators are 2, so if you multiply, they cancel. So that actually works out pretty nicely. So that cancels, and so you're left with X minus 1 that drops down, and a plus 1 here. And so if I simplify, these two will cancel, leaving me with just X. So I just get X, which is good. That means that this here is an inverse function. As long as it's 1x to the first power, that tells me that this is an inverse. And you should get the same result if you had done g of f of x. You should have gotten an x as well. So it doesn't matter which one you choose. So I'm going to say, yes, they are inverses. Okay, let's try out this one. And this time I'm going to be a little bit more strategic on which one I would use to plug in, because I notice I have a lot of roots, I have a lot of powers. This is the part where you might want to be a little bit more thoughtful in your math work. So first off, I can do the same as before. I can plug plug this g in for x. But that would mean I would have to square everything, and that's quite hefty. So perhaps it's easier this time to plug f into g so I don't have to square anything. So I'm just going to choose the other way because I haven't done it the other way either. So I'm going to choose where I plug f into g. And so that would mean that I would be taking g, and this would be x squared. That would get replaced since f is x squared plus 4. And so I'm going to plug all of this in for g, but the only x here is this guy that's under the root. So when I rewrite this g, it's going to be the square root, but instead of that x, I need to write x squared plus 4, what I'm plugging in. And then there's still a positive 4 outside, so let's carry that down. Now, when I see this here, I notice like, wait a minute, I can't take the square root of x squared plus 4. Like, I can't take the square root of these two separately because they're joined together. So that means I can't do anything. Like, I'm stuck. Like, I can't reduce this any further. I can't even break these two up and try to square them. That doesn't work for mathematics. So in this case, square roots are also very tricky to make inverses of. So in this case, this is all I'm left with. So I didn't even get close to getting x. So this is definitely no, not an inverse. But how about we double check? We could always find the other version, which is f plug in g of x, and see if maybe it's just this equation that doesn't allow me to simplify. Maybe the other equation is better. So if I go back and I replace g of x with what it is, which is square root of x plus 4 into f, that would mean I'd be taking this x and plugging all of that in for that. So use your parentheses, square root of x plus 4, but then you have to square it because that x squared is a square, plus 4, that was to the side. And this looks awfully messy. So one, I have to FOIL this part out, so because you guys might remember anytime you have something that's squared, you have to FOIL it. So I can already tell this is going to be a mess. X times x, if they're both under a square root, they come out just as x. Square root of x times square root of x comes out as just x to the first power. Because anytime you have a square root, you combine the inside together. So x times x is x squared. and a square root and a root cancels each other, and that's how I got the x. X times 4 is just going to be 4 square root of x. 4 times a square root of x is another 4 square root of x plus 16. 4 times 4 is 16 plus 4. All right, this here just looks like a jumble mess. Like these 4 square root of x are not going to cancel. Neither are these going to cancel. So I can just tell you right now, I'm just going to stop right here. This is not going to end up being just an x. This is a jumbled mess. So this is definitely not an inverse, and I've already checked both ways. So this is just not an inverse, which makes sense because you have square roots here. Square roots are hard to become inverses. And we can talk about that next time. So I am going to make a video for the practice problems, so stay tuned for another video if you want to see how the practice problems are done. I'm going to walk you through that in the next video. Bye, guys.